Good morning, students. So, in this short video, we are going to see the theory part of Helmholtz resonator, whose experimental side I have already recorded, and you will be seeing that next. So, here we are going to see the theoretical modeling of an Helmholtz resonator. So, in my presentation, the video which I have recorded uh, as a live demonstration of doing the Helmholtz resonator in the lab, I have symbolically taken one of the bottle and demonstrated you the uh, this bottle can act as a Helmholtz resonator. So there I have shown you that the when I put some water inside the bottle and blow it, the sound is different from without water. Then I have changed the water level, and you can see that the frequency of the sound is increasing as I increase the level of water. That means I am actually decreasing the level of air column. So when I decrease the level of air column, the frequency increases, right? So it's an inverse relation. But this inverse relation is no need to be a linear one. We don't know what relation is this. We have just got that when you decrease the volume of air column, the frequency increases. Is it increasing linearly or non-linear fashion? That we have to see. So for that kind of deep understanding, one has to model it, the Helmholtz resonator. Okay, so when you take a bottle like this, when you are modeling the Helmholtz resonator, you see that you have two parts. One is the neck, and another one is this cylindrical air cavity, right? So these two parts have to be distinguished separately. Okay, now I have symbolically drawn a figure of bottle here, and see, this is the bottle, and if you look at this, yeah, this is a bottle. So uh, see, there is a neck here, and that neck, there is some air molecules is there, and that air molecule have some mass, right? So that mass is called acoustic mass. Okay, so when you have a driving force, like when you excite a tuning fork and keep, so what is you are doing is you are pushing that air down. So the neck part, there is an air which you call acoustic mass. It's actually not the mass in the conventional sense. This mass is pushed down, and the air inside the cavity, which will actually act, you know, a force against this. So there is a reactive force will come, and that force uh, is actually like a spring. So you can actually model this Helmholtz resonator as a one-dimensional, as a system with a one-dimensional degrees of freedom, like mass and a spring. Uh, right. So this is what the simplest model what we are going to do. Suppose, see, there are a lot of applications for Helmholtz resonator. As I was mentioning you some of the applications in the demonstration, uh, that perforated absorbers in the auditorium. You have cars where they use the Helmholtz resonator, or the violin, guitar, and all will have a hollow part. On that you have strings, right? This hollow air in the hollow part, there this that part behaves like a Helmholtz resonator. So many things around your you can actually relate this Helmholtz resonator. Okay, So this is one of the simplest model as a stepping stone. If you really want to model it, it's quite complicated. Such kind of models are called lumped parameter model, and we are not going to do such detailed analysis. And of course, when you are going to study a topic on acoustics, mostly mechanical engineering students probably will study in future, or how to design you know a Helmholtz resonator with an industrial standard. But as a first year BTech students, it's good to know how we are going to model a simple system with very, very simple assumptions. So one of the assumption is what I told you is that the air in the neck is considered to be a mass element, acoustic mass, and the air in the cavity which which exert a reactive force when you push the air down, that behaves like a spring. Okay, actually here itself you can improve your model by, there will be an inertia for this mass in the neck, so you have to add a what you called a frictional force there, damping force there. And when you put a some driving force on the top, like uh, you know like this one, tuning fork, there you have to have a driving force will be there, then there is a damping force will be there, so force damped oscillator. So you can actually solve that differential equation, and we can improve upon your model, but we will not do those things. We'll take a simple you know one dimensional mass spring system. We'll treat it as a one dimensional mass spring system. Okay, now uh, now if you want to really apply the Newton's second law to this problem, and you know uh, you have to have a differential elemental model where we will construct a force model for this. Okay. So when you blow the air, or when you push the air in the neck, it push down, right? When you push down the air element or that mass element down, the volume actually decreases, where the main cavity's volume slightly decreases. Okay, so this process take place so fast that the system will not get any time to exchange heat energy from the system to the surrounding. So this happens so rapidly, and the system cannot exchange heat with the surrounding. Such kind of process is called adiabatic process, and this is an adiabatic process. And when you decrease the volume, the pressure increases. Okay, and inside. So the PV raised to gamma for any adiabatic process, you might have studied in your 12th standard that PV raised to gamma is a constant, where gamma is a factor called Cp, the ratio of Cp by Cv, and that is basically for a diatomic molecule, a gas with a diatomic molecule, which is 1.4. And our air is mostly a diatomic in nature, like oxygen, nitrogen. So you can take that value confidently as 1.4. And okay, if you want to construct a differential element, you differentiate it. So you can take delta P V raised to gamma plus P gamma V raised to gamma minus 1 into delta V equal to 0, because right hand side of this is constant. Now you take the you can actually rewrite this equation. So I have drawn a picture here which can be clear, which will be more clear to you. So there is a cavity here, the blue shaded is a cavity, and there is a small neck, that is something like the neck part of the bottle. Okay, so the area of that small neck part is a suffix x, and the length of it is capital N. And the volume here refers to the volume of the blue shaded region. Okay. Okay, now we get an expression for delta P by P, which is equal to minus gamma delta V by V. It's very simple. You take the above equation, transpose it to the right hand side because it is 0, then there will be minus sign will be there. So you have delta P by P and V gamma will come in the denominator. So there is a V gamma minus 1 in the numerator, so it cancels out. So you'll get V. Okay, so delta V by V on the right hand side. Okay, two, three things one has to be taken care. This is a detail, but the the wavelength of the sound. Okay, that's why the lambda s should be much greater than. Obviously, in our case, it is true. Lambda s should be much greater than ax, and also it should be greater than the small the neck. The length of the small neck is capital N. So this should be more. And also we assume that the change in pressure, you know, near the neck when you push the mass down, the main cavity's volume slightly decreases, and so it induces a pressure delta P, which is at any instant is same everywhere in the cavity. Okay, that also we assume that. These are details. If you don't assume this model is may fail. Okay, so the deduction in the volume, this delta V, okay, this deduction in the volume delta V is actually which one can write it as the cross-sectional area times the length of the oscillating air column delta X. So when you push it, the air column in the neck moves a delta X distance. Okay, that into area AX is the volume delta V, which is the decreasing, right? We are compressing it. So the volume in the main cavity decreased by this much volume. So the restoring force, if you want to calculate the restoring force, that is equal to delta P into AX. That is actually the restoring force created. Of course, pressure into area is actually force, you know that. So the restoring force here is delta P into AX, where AX is the area of the small neck part. Now I substitute my delta P from the equation the above, that is delta P by P equal to minus gamma delta V by V. So if you want to calculate, substitute for delta P, you multiply this P on the right hand side. So minus gamma P delta V by V. Okay, minus gamma P delta V by V into AX. So that is the restoring force. So minus is actually obviously will show you that it's a restoring force. So this delta V is actually, I told you, is AX times delta X. So I have written it that. So the restoring force F is minus gamma P AX square delta X divided by V. Now Newton's second law. What is Newton's second law? F is equal to m d square x by dt square. So m into d square x by dt square equal to, so this force model which we have constructed now equated to the fundamental definition of second law, which is m d square x by dt square, which is equal to minus gamma p ax square delta x by v now. Now you can take this delta x outside and keep minus of something. So there is this, obviously now you can actually infer that this is something like f is equal to minus k delta x, where k is the, the spring constant. So you actually evaluated the spring constant. So I told you when you have a one-dimensional spring mass system, the frequency is actually omega equal to minus k by m, right? Minus k by m. So now in this particular system, what is this k? We have actually got it. Okay, from the equation 1, if you look at this inside the cross square bracket, whatever it comes, that's actually k. Now you also know that velocity of sound as an expression that gamma p by rho into all power half, where rho is the air density. Now, the in general the mass in the neck, okay, you can write it as the ax into L, that's a volume, into the density. But here you should actually, this is an approximation, you should remember that the length which we use, a capital L, that is also a approximation, and the mass also, the effective mass and the effective length are actually different. And that comes from the, as I told you, if you really want to do, it's called lumped parameter model. It depends on the geometry of the neck and various other factors. Okay, so as I told you, it's the simplest way of understanding the physics of Helmholtz resonance. So I am actually avoiding all complications. Okay. Now, the velocity of sound is gamma p by rho into all power half this velocity. So now F is equal to minus k delta x. If you have a force model like this, the restoring force is proportional to displacement, then it is a simple harmonic motion, right? And this is a Hooke's law. Okay. Now, of course, you can actually see that omega is square root of k by m, 2 pi nu is square root of k by m, nu is 1 by 2 pi square root of k by m. I substitute what is k there, and my nu is very simple now. Okay. Now, what is my nu is this one. Then there's some simplification. I have cancelled ax on both sides, and I have substituted for gamma p by rho as you know this m, k by m I have substituted ax rho into L, so ax get cancelled, and you will have gamma p by rho is v, square root of that gamma p by rho square root is actually the velocity of sound, so that will come out, and inside the square root you have ax divided by vl. Now, what in the laboratory we are doing? We have a bottle filled with water. We are slowly removing water. We allow the water to drain out, and we excite a tuning fork and keep. That means you are varying the air column which is resonating, which is going to resonate with the frequency of the tuning fork. Okay. Yes. Now, if you look at this expression here, this AX is actually the, you know, small area of the neck part, and L is its length, length of the neck part. But then that is fixed, that's a constant. V of S is also, velocity of sound is a constant, 2 pi is a constant. So what is it actually? Only V is the variable there. V is varying by varying the amount of water, right? So this is what we are going to see in the my demonstration. We are draining out water. Okay, so if you look at that, everything else is a constant, then you can easily see that nu square V is a constant, right? You square on the both side, so everything is a constant divided by V, so nu square into V is a constant. Now, this is what the derivation of that expression. So this is, first thing is you are going to verify this relation whether nu square V is a constant. Second one is, assuming that this relation is true, you will actually find out the volume of the resonating air column corresponds to a non-tuning fork. Okay. Then from that information, assuming that nu square V is a constant, you will find out what is its frequency. Okay, so this is how we are going to do. So we in the lab, you are going to do the experiment with 5 tuning fork. Okay, 4 of them whose frequency is given to you, and we can see the frequency in the bottom of the tuning fork. You can read off, And okay, so corresponding to this all four, you are going to do the experiment and find the volume of the air column, resonating air column, by doing the experiment, by measuring the water, how much water has collected before you listen that sound. Okay, now that is for four tuning fork. Now the fifth one, the unknown one, you can actually find out the volume of the air column with which it is resonating, and the loud sound you can experience, and you can find out the volume of the resonating air column. Okay, now you take a graph sheet, you plot the x-axis, the 1 by frequency square. So you have actually for tuning fork there, so you will plot that 1 by frequency square in the x-axis, and you have a as the y-axis, you have the resonating air column. So that you will mark here in the y-axis. Now, the unknown, the volume corresponds to the unknown tuning fork. Volume of the air column which is resonating for the unknown tuning fork is, let us say, it is somewhere here. So what will you do? So first thing is you have the volume and the 1 by frequency square. So of course you will get these points like this, right? 1 2 3 4. Then you join the 4 points with a straight line. You will best fit the line, so you will actually realize that okay, n square v is a constant, it's a straight line. Okay, this relation you will verify. Now the vx is here, then you draw a line which is parallel to the x-axis where it is cutting this relation. N square v is this point. Then you extrapolate down, and where it touches the x-axis, that will be 1 by nx square. So the v of x, the corresponds to unknown volume. What is this? 1 by nx square. So 1 by nx square you read off from this graph sheet, and you calculate what is nx, what is the unknown frequency. So this is what you are going to do in the lab. So typically a tabular column of your experiment looks like this. So you have, I told you there are 5 tuning forks. So 4 you can actually read off its frequency values. So 1, 2, 3, 4. So you note down initially all the frequencies. So the way I have written here in this tabular column, so before doing the experiment, I will arrange my forks. In what way I will arrange? Because when you start doing the experiment, your bottle is almost filled. Apart from the small neck part, the main cavity part fully water is filled. That means the air column volume which is going to resonate with the tuning fork is almost nil. So you are going to create now that volume slowly by removing the water. So initially the air column volume is less. That means the frequency should be very high, because n square v is constant. So when v is small, capital V is small, the frequency should be very high. So normally you should start with a very high frequency. Okay, you will start with a high frequency so that you will first get for a small volume of the air column, you will get a resonance frequency. So you should arrange in that fashion. Otherwise, what happens if you start with, for example, if you start with 256, so you have to drain so much of water down to get the resonance point. Then you have to refill it again. Then you have to take, suppose the second one you have taken 480. So no, after 500, then you have to refill again. Then you do it 160. So it's going to be a unnecessary time, unnecessary expenditure of time. So lab is only for 2 hours for each experiment. Okay, so that is what one has to do. Um, Okay, sorry that yeah. Now yeah, so you have to do this in this order. 480, 384, 280, 256 in the descending order of the frequency of the tuning fork given to you. That is better. Now the next step, now this information is there before you come to the lab. Now after that you can actually calculate 1 by n square. You have calculator, so frequency is given, so 1 by n square you can calculate. That is the third column of the tabular column. Now what is the fourth column? It's a resonating air volume. This you have to actually do perform the experiment and obtain. So this is these four values only what you are going to do it in the lab. Now if I have demonstrated one, and I have got, if you remember, next time, next first this is theory video, next is actually experimental. When you see that I have got the resonating air volume as 155, that is corresponds to 480. This student has done it. I have taken from one of your senior batch student whose record book which I have taken a photograph. Okay, so this student has got 160. I have got 155. So probably I am little more accurate than him. You can see that, he is getting, see, when you multiply n square v, it's going to be, a 7-digit number, or 8-digit number, 1, 2, 3, 4, 5, 6, 7, 8-digit number. You have to keep all the digits. Now he is getting 3686. Now this n square v should be a constant, but it's slightly varying from actually third decimal, fourth decimal variation is okay, no problem. But the second reading you see corresponding to 384 is getting 37. This kind of mistake definitely will be there. Okay. So we are actually not going to evaluate a lab report based on the numerical values which you are going to get. Okay, the way you perform the experiment, if somebody, see, for example, if somebody is doing a simple pendulum experiment and 2 pi into square root of L by G, and measuring the period of the oscillation of the simple pendulum, you have to evaluate what is the value of G. Okay, you can measure the length. So only way, it's a one-dimensional problem, a mechanical system with only 1 degrees of freedom, and only one length scale is there, right? Everything else is. So by measuring the length, you're going to varying the length, you can find out actually that change the period, and you can actually find out the G value, which is actually 9.8. If in the lab, if somebody get exactly 9.8, then there is some problem. I don't think he has done a you will never get it. When you actually perform an experiment, there will be an error bar, there will be a scattering in the data. That's no problem. But more or less, this value n square is a constant. Okay, so I got a value when I did the experiment is 155. I also may not be exactly the correct. Okay, so this is what the joy of doing an experiment by your own. Okay, and okay, so you will get n square v. So these are the points which you can actually plot in the graph sheet. Okay, so now one more thing you have to calculate is the you have to take the average of it, n square v average. Mean value also one can calculate. Actually we are not going to use it, this n square v mean value, but you can actually calculate if you are interested in the error analysis and other stuff. One can actually calculate the mean and the difference from the mean value by the absolute value. You can actually calculate the percentage of error. It's okay, that's a separate topic. Now you will also calculate for the unknown tune, for unknown frequency, the tuning fork with an unknown frequency, you will calculate the volume, resonating air volume, right? That also you will calculate here. You calculate. So this is the observation or tabular column. Okay, now you will take a graph sheet. So the graph sheet, graph plotting is a very important aspect. That is what you are going to learn in this lab. Okay, uh, so all these seven experiment which you are going to do in the laboratory, unfortunately this is in a virtual mode you are going to do, but for every experiment there is a graph has to be plotted. Okay, now the record book, there will be a big graph sheet. You use the entire graph sheet to plot the graph. That is the first advice. The second one is you have to write the title of the experiment. Helmholtz resonator. Okay, the graph is a self-explanatory. It should be self-explanatory. If somebody see your graph, and the person who is going through the graph should know every information. Okay, so this is also again I have taken from an indicative graph from a student, one of your senior student who has completed it. But because of pandemic, by the time the institute has closed down and you cannot evaluate it. Okay, so that's why there is no red mark and other things here. Okay, now the x-axis is 1 by nx square. So there is some problem in this graph. I have taken this graph to tell you that how you should actually draw a real graph. So the axis of the graph is marked as, physical constant which you are going to plot, indicative symbol for that, and the unit. This is the way one should actually mark the axis. So here the students have done 1 by n square. So this is not quite correct. So you have to write here actually 1 by frequency square. Okay, in bracket you can say the unit is 1 by hertz. So symbol also you can write here 1 by n square. Okay, so frequency square, what is actually the physical quantity, and representative symbol here 1 by n square, and the unit. These three things should be there. Here also in the y-axis you have just written V in CCC, cubic centimeter. Instead of that, one has to write here the resonating air column in V in cubic centimeter. So this is the way one should actually mark. So you have, I told you, you have 4 points. So the student have done a very decent job of fitting these 4 numbers. I have not actually gone through whether each value, whether whatever he has got is he has plot, but in real lab we will check it. Okay, and it is not that the graph is just connecting the points, experimental data points. No, it is actually best fit. That means no, not even a single point need to be on the line. But the line, if it is not, if the points are not in the line, it's fine, no problem. But the distance, it is, all the data points which is away from the line should be as short as possible. That's why it's the best fit line. So when you have a points like this, you are going to fit a line, right? So these days, all graph plotting softwares actually the best fit option is inbuilt. Okay, so you can actually do these things in Excel. It will fit and give you the straight line and give you what is the slope of it, every other parameters it will automatically tell you. Anyway, but in the laboratory you have to draw it in on your own, and you have to plot it. So it's actually best fit line. Okay. Now you got a straight line, you have verified it. Now the unknown volume which the student again forgot to mark, it's Vx, the unknown volume you have. And now what is the aim? You have to calculate what is the unknown frequency of the tuning fork. So what you will do, you have draw a you have to draw a line, straight line parallel to x-axis where it is cutting here, and you extrapolate it down. So you have 1 by ns square. So actually you have to write, the student have to write here 1 by nx square is with unit. So units are very important. Okay, units are very important. Whenever you represent a physical quantity, it has to be uh, with unit. Okay. Now, most of the other graphs, when you are going to see the other experiment, also whose video and presentation you are going to see, there also, in many cases, you are going to find out the slope of some quantity, a slope from the graph. Okay. Now, for a mathematician, the slope has no unit because it is dy by dx, right? But in physicists, when you plot a graph, the x-axis and y-axis contain some physical, you know, quantities which is dimensionful. So when you take the ratio of it, you will have the slopes will have some unit. So you have to write that. Okay. Now, the scale. So graph, the scale you have to mention. What is the scale you used in x-axis? What is the scale you used in y-axis? Okay, so that has to be very clear. So these things has to be taken care when you plot the graph. So what are the three things? Title of the graph, the way you mark the x and y axis, right? Physical quantity, representative symbol, unit. Then you have to do a best fit line, right? Then, the scale, units. So these things are very important. Okay, so I think I will stop here my presentation. So thank you everyone. So one more point. So when you use a tuning fork, the tuning fork vibrate with some frequency, and the air in the column also start vibrating. So at the resonance point, the maximum energy transfer happen, and the movement, the vibrating movement is what you are going to, the loud sound you are going to see when both couples. Okay, this is what you are going to see. But what happens when I blow this bottle? This I told you, this also can be actually behaves like a Helmholtz resonator. So there is no, so this is slightly different. Okay, when it act like a vessel, when I blow air, the mechanism is slightly different. Okay, when I actually blow this, when I actually blow this, I am actually, pushing the air past this opening very fast. So Bernoulli's principle, as you know, that when I, create a flow of fluid with a very high velocity, the pressure there is actually decreases. So actually the air inside the cavity rushes out, right? Because of it's rushing out, the pressure inside the cavity decreases. So suddenly, the pressure, outside pressure pushes the air back into this. So after some time, it actually, this pushing of air, uh, you know see, there is a inertia for this. So when this pushes out, it goes some distance, then by the time the pressure decreases in the cavity, the outside air molecule pushes it back, right? So this is like a simple harmonic oscillatory motion, and that vibration is what it act, his frequency of that vibration is what you are going to listen to when you use this as a vessel, when you use bottle as a Helmholtz resonator. And it's a doable exercise for you. You take a bottle, uh, and in any bottle you can approximate here the neck area, you can calculate, right? How will you calculate? You take a small piece of uh, thread, and make a measurement of the circumference, and from there you can calculate the area, right? Because this is 2 pi, you know, 2 pi r. So you can calculate what is the radius. So pi r square is the area of this, so you can calculate it. What else you want? Vs. So frequency is equal to Vs, the sound velocity in air, divided by 2 pi square root of Ax, that you can calculate, by VL. L is this neck length. You can actually calculate again by using a scale. It's an approximate value. Okay, no problem. But then you can calculate this volume. Assume that this is cylindrical one, right? Calculate the area here and multiply by the length, you will get the volume. So you can actually calculate the frequency. So what you do is you collect some bottle at home, different bottles. Okay, this is one exercise you can do, and calculate the resonant frequency of each bottle. Okay, approximately you can calculate. Or you take one bottle and fill the water at different level, and find its frequency. That also one can do. So various things you can try, and you can verify the formula. You can verify n square v is constant, right, by filling water. So this experiment, you don't have to come to NITK to perform it. You can sit at your place and do and make a feel for it. Okay. So it has got a lot of applications, as I told you. So I'll stop here, and thank you. Have a good day.